Picture this. It's the late Jurassic, approximately 150 million years ago, and a massive herd of sauropods, the largest animals ever to walk the Earth, crosses a sprawling floodplain, their footsteps sending tremors through the Earth. Among them is Camarasaurus, the most abundant sauropod of its ecosystem. Fossils from the Morrison Formation show it could reach 23 meters long, weigh over 40 tons, and strip entire trees bare in minutes, yet hiding a vulnerability no amount of size could protect. To understand how Camarasaurus came to dominate the late Jurassic, we need to step back more than 50 million years, to a time when its colossal lineage was just beginning to rise. The story begins in the early Jurassic, around 190 million years ago, when the continents were still joined in the supercontinent Pangaea. Much of the land was a patchwork of open floodplains, fern prairies, and towering conifer forests. It was in this world that the first true sauropods emerged, descending from earlier smaller plant eaters known as prosauropods. These ancestors still carried some traits of their bipedal past, but evolution was already reshaping them for a very different future. Their bodies grew longer, their necks more flexible, and their limbs began to transform into weight-bearing columns. By the Middle Jurassic, sauropods had spread across the globe, reaching sizes no land animal had achieved before. Fossils from the Shaximiao Formation in China and the Forest Marble Formation in England reveal species that stretched over 15 meters, their skeletons already displaying the innovations that would later define the giants of the Morrison Formation. When the late Jurassic arrived, sauropods entered their golden age. North America's Morrison Formation, a vast swath of sandstone and mudstone that stretched from New Mexico to Montana, became home to some of the most iconic dinosaurs in history: Diplodocus, Brachiosaurus, Apatosaurus, and most numerous of all, Camarasaurus. Why Camarasaurus thrived here is still debated, but its fossil record is unmatched. More than 75 individuals have been recovered, from fragile juveniles to adults weighing over 40 tons. Its name, chambered lizard, comes from the hollow spaces in its vertebrae, part of a network of air sacs that ran through its body, making it lighter than its size suggested and feeding its enormous lungs with a steady supply of oxygen. Every part of Camarasaurus was a lesson in efficiency. Its neck could reach over 10 meters, sweeping in slow arcs across multiple feeding heights without the animal needing to take a single step. Its legs were thick, vertical pillars, capable of holding up a frame heavier than a modern humpback whale. The head at the end of that vast neck was small, with simple, spoon-shaped teeth perfectly suited to stripping leaves and needles from branches in a single bite. There was no chewing. The vegetation was swallowed whole, to be broken down later in the immense fermentation chambers of the gut. Inside, the air sac system worked in harmony with its hollow bones, pumping oxygen continuously through its body, allowing it to keep moving, feeding, and breathing with relentless steadiness. Evolution had created the ultimate harvester of plants, a living engine of bone, muscle, and hunger. But the real story of a sauropod wasn't just in what towered above the trees. It was hidden deep inside, in a body so vast and specialized that its own inner workings held the key to both its triumph and its downfall. Inside a sauropod, everything was built on a scale that defies imagination. The skeleton alone was an architectural masterpiece, a framework of bone designed to carry 40 tons or more without collapsing under its own weight. The vertebrae were honeycombed with air-filled chambers, each one lightened by the same network of pneumatic sacs that kept the animal breathing. This system, similar to that found in modern birds, meant that even an animal the length of 2 city buses could inhale and exhale in a continuous cycle, never pausing to catch its breath. Its heart was a biological pump of extraordinary power, likely weighing hundreds of kilograms. To send oxygenated blood up a 10-meter neck to the brain required blood pressure far beyond that of most animals alive today. Some paleontologists estimate that a sauropod's blood pressure may have exceeded 500 millimeters of mercury, more than 4 times the average human's. a feat that would have demanded thick, muscular heart walls and possibly even accessory pumps along the neck. The digestive system was no less extreme. Camarasaurus and its relatives didn't chew. Their simple, chisel-shaped teeth merely stripped leaves, which were swallowed whole. The real processing happened in the vast fermentation chambers of the gut, where symbiotic bacteria broke down cellulose over days or even weeks. This slow, constant digestion released the calories needed to keep the enormous animal alive. But it also meant carrying a belly full of fermenting plant matter at all times, adding even more weight to an already massive frame. And then there was the brain, proportionally small, perhaps no bigger than a cat's, yet perfectly adequate for a creature whose survival depended on feeding and moving rather than complex problem-solving. This was a body optimized for one purpose: to eat enough to sustain its size. Everything else, from its lungs to its limbs, existed in service of that single goal. But the very design that made sauropods invincible to predators also bound them to a delicate balance. To fuel such an immense biological machine required not just food, but a near-constant supply of it, and any disruption in that supply could push the system toward collapse. And in the late Jurassic world, disruption was never far away. In the late Jurassic, the Morrison Formation stretched like a green ribbon across what is now the American West, a patchwork of river deltas, open woodlands, and seasonal floodplains. This was the stage on which Camarasaurus became the undisputed workhorse of the sauropod world. It wasn't the longest or heaviest sauropod of its time. Brachiosaurus towered higher, Diplodocus stretched farther. But Camarasaurus was everywhere. More than 75 individuals have been uncovered from Morrison sites in Colorado, Utah, and Wyoming, making it the most abundant sauropod of the formation. Its bones, often found in near-complete skeletons, tell us more about sauropod life than almost any other species. The skull was short and deep, unlike the long, low heads of its cousins, and packed with spoon-shaped teeth that could shear through tough vegetation. These teeth were worn down and replaced regularly, a crucial adaptation for an animal that may have consumed hundreds of kilos of coarse plant matter each day. Stomach contents preserved in a few rare specimens reveal a diet heavy in conifers, cycads, and ferns, with no sign of the soft, lush leaves that dominate modern forests. This was a creature built to process whatever the season provided, no matter how fibrous or unappetizing. Fossil evidence suggests Camarasaurus traveled in herds, perhaps for protection or to exploit food sources on a massive scale. In times of plenty, a group could move slowly across a fertile valley, stripping the treetops and undergrowth alike. But in the Morrison's semi-arid climate, plenty never lasted. Geological studies of the formation's sediments show clear cycles of wet and dry seasons, with long stretches of drought transforming rivers into muddy trickles and forests into dusty plains. For giants that depended on constant feeding, these lean months were deadly. It's here that the vulnerabilities of gigantism start to show. A smaller herbivore could move quickly to new feeding grounds or survive on less food for longer. A 40-ton sauropod could do neither. It had to keep moving and it had to keep eating. And when resources failed, entire herds may have starved where they stood. In the Morrison Formation, survival for a giant wasn't about avoiding predators. It was about finding enough to eat before the land went bare. The fossil record paints a clear picture. These floodplains and forests were not a constant paradise. Instead, they cycled between fertile wet seasons and punishing dry spells, a rhythm written in the alternating sandstone and mudstone layers laid down by ancient rivers. During the rains, Camarasaurus herds could fan out across lush lowlands, feeding on tall conifers and mid-level cycads while smaller herbivores grazed the ferns and horsetails below. But when the climate shifted toward drought, the transformation was rapid and brutal. Vegetation withered, river channels shrank, and the dust carried by seasonal winds settled over the land. In these months, even the highest treetops could be stripped bare long before the herds moved on. Competition only made the struggle sharper. The Morrison was home to a whole cast of mega herbivores: Diplodocus, Apatosaurus, Brachiosaurus, each with overlapping diets and enormous appetites. Isotopic analysis of fossilized teeth from multiple sauropod species suggests subtle differences in feeding height and plant preference, a kind of ecological truce that reduced direct competition during good times. But when the greenery thinned, those differences collapsed. Every giant was after the same few remaining food sources. For a creature weighing 40 tons, losing access to food was a rapid death sentence. Unlike smaller dinosaurs or mammals, Camarasaurus couldn't simply switch to hidden reserves like seeds or underground tubers. Its entire physiology, the long neck, the air sac lungs, the massive fermentation gut, was tuned for a steady, high-volume intake of fibrous leaves. Deprived of that flow, the biological machinery slowed, digestion faltered, and the animal's own weight became its enemy. Predators rarely posed a threat to healthy adults, but drought could turn even an apex herbivore into an easy target. Bone beds in the Morrison contain the remains of multiple Camarasaurus individuals alongside teeth of Allosaurus and Ceratosaurus, suggesting that weakened or dying sauropods were scavenged or hunted outright when their defenses failed. And yet, the greatest danger wasn't the teeth of predators. It was the empty space where the leaves used to be. In an ecosystem where giants ruled, the land itself could turn against them, and every dry season was a roll of the dice. For millions of years, gigantism had been the sauropod's ultimate defense. Sheer size kept them safe from predators, allowed them to reach food others couldn't, and gave them the digestive capacity to survive on low-nutrient plants. But the very traits that secured their dominance also made them fragile when the environment shifted. Reproduction was one of the clearest trade-offs. Unlike mammals, which invest heavily in a small number of young, sauropods relied on laying dozens of eggs at a time. Fossilized nesting sites from the late Cretaceous of Argentina, thought to represent titanosaur relatives, show shallow scrapes filled with eggs, each about the size of a soccer ball. While this strategy produced many offspring, it offered little protection. Hatchlings were tiny compared to adults, vulnerable to predators and environmental hazards, and few survived long enough to replace a herd lost to drought or famine. Mobility was another limitation. Moving a 40-ton body across vast distances in search of food took enormous energy. Trackways from sites like the Purgatoire Valley in Colorado suggest that sauropod herds traveled at only a few kilometers per hour. In good times, this slow pace conserved energy. In lean times, it meant herds could be trapped in barren landscapes, unable to reach the next patch of vegetation before hunger set in. Then there was metabolism. Sauropods may have been mesothermic, neither fully cold-blooded like modern reptiles nor warm-blooded like birds and mammals, but their sheer mass meant they retained heat efficiently. This thermal inertia helped them survive cooler nights, but also demanded a constant intake of calories to maintain internal stability. Any break in the food supply risked not just starvation, but a dangerous spiral where body temperature, digestion, and energy levels all declined together. Even their feeding adaptations had limits. Specialization in high-volume leaf stripping meant they could exploit abundant forests, but it left them poorly suited for dietary flexibility. Studies of tooth wear patterns in Camarasaurus show heavy abrasion consistent with tough, silica-rich plants, an advantage when those plants were common, but a disadvantage if softer, more seasonal plants dominated after a climate shift. In the balance sheet of evolution, gigantism had always paid off, until the environment stopped paying into it. And when the cost outweighed the benefit, even the largest creatures on Earth could be brought low.